Hi guys, in the last lecture we started with the study of transient stability. We first saw that the transient stability is concerned with determination of stability when the system suffers large disturbances. And I told you large disturbances may be due to fault or contingency. Then we saw that transient stability study is done to determine the operating time of circuit breaker, which must always be less than critical clearing time. What was the critical clearing time? It was the maximum time at which a fault can be cleared to ensure that the system remains in synchronism. Then we studied about assumptions in transient stability analysis. There I told you have to neglect the effect of AVR and speed governor so as to do the worst case analysis and determine the stability. Then we saw power transfer, where I told you whenever a fault will occur, then what we will consider is that the reactance changes. So we define three reactances, one before the fault, during the fault, and after the fault is cleared. And similarly we define three Pmax, Pmax1, Pmax2, Pmax3. This was called as transient stability limit and the other two were steady state stability limit. And the last we saw was equal area criterion, which was a special case of swing equation for single machine or two machine system, which stated that integral PAD delta must be 0. That is, area under the accelerating power curve must be 0. So in this lecture we will consider different cases of transient stability analysis and we will try to apply the equal area criteria to each and every problem so as to determine the stability criteria. Okay. So the first case is when we increase the steam input of the machine suddenly. So first of all, in all the cases of different type of faults, we will consider the steam input as constant. So this is for the illustration purpose that we are considering that the shaft input of the machine has been increased suddenly. Now initially the shaft input of the machine was PS0. It has been increased suddenly to PS1. Now as I told you, under steady state, what happens is shaft power should be equal to electrical power. Now this curve here, this represents electrical power and this is my shaft power. So initially the machine is operating at an angle delta naught. Now when the shaft power has been increased to PS1, the intersection moves to the point delta 1. That means the new steady state value should be delta 1. So we have to go from delta naught to delta 1. Ideally what should have happened is the delta should have increased from delta naught to a value delta 1. But let us see what happens in practically. So when shaft input is increased to PS1, so here we will make use of two equations. One is your swing equation, h by pi f d square delta by dt square, shaft input minus electrical output, and other equation is d delta by dt, which is equal to omega minus omega s. Now let us see at point A. What happens is shaft input goes to PS1, but electrical power cannot change suddenly, it remains PS0. So PS1 is greater than PS0, that is shaft power is greater than electrical power. Now since shaft power is greater than electrical power, from swing equation what I can say, d square delta by dt square is greater than 0. So that means rotor will accelerate. Now under steady state what happens is speed should have been equal to synchronous. Now when the rotor will accelerate, speed will become greater than synchronous, due to which d delta by dt will be greater than 0 and delta will increase. because for an increasing function the slope is always greater than 0. So if d delta by dt is greater than 0, we can say that delta increases. Now if delta increases, we will slowly move from A towards B, okay, as delta increases. So when we are moving from A to B, in the region A to B, this is my electrical output, but mechanical input is this. So mechanical input is always greater than electrical output. PS1 is greater than P. So what will happen is that d square delta by dt square is always greater than 0. So that means rotor will accelerate from A to B. So speed will increase. And if speed increases, then what will happen is omega will become greater than omega s. D delta by dt will be greater than 0. So delta also increases. So as we move from A to B, delta will increase. Now as soon as we reach point B, then what will happen? As soon as we reach point B, now at point B, we have the intersection of electrical and the mechanical power. So PS1 is equal to P, due to which d square delta by dt square should be 0. So that means speed becomes constant. Okay, because acceleration is 0, so speed will be constant. Now when we were coming from A to B, the speed was constantly increasing. At A, speed was synchronous speed, and as we moved towards B, the speed kept on increasing. That is, suppose synchronous speed is 1000 rpm. As we are moving from A to B, speed increases. So let us say at point B, I have 1500 rpm. But speed at B is definitely greater than omega s. Because from A to B speed was increasing, at A it was omega s, so at B it will be greater than omega s. So d delta by dt will be greater than 0. So delta will increase. That means we will go beyond B. Okay. Ideally, when we were coming from A to B, we should have stopped at B, but here we will go beyond B because delta is still increasing. Now if we go from B to C, what happens is, this is my mechanical input, but this is the electrical output. Definitely electrical output is greater than mechanical input. From B to C, electrical output is greater than mechanical input. So d square delta by dt square is less than 0. So rotor will decelerate. That is, speed will start reducing. Now at point B, speed was greater than omega s. Let us say omega s is 1000 rpm. Then at point B, we had a speed of 1500 rpm. Now the speed starts decreasing. But say until it reaches omega s, the speed will go on reducing. So from B to C also, though the speed is decreasing, but still it is greater than omega s. That is, it is decreasing from 1500 rpm towards 1000 rpm. But still it hasn't reached 1000 rpm. That is, it is going from 1500 to like 1400, 1300 and 1200. But still it hasn't reached 1000. So doesn't matter whether the speed is increasing, decreasing, it is still greater than omega s. So d delta by dt is greater than 0 and delta will keep on increasing. Now the significance of point C is such that when the speed is reducing, suppose C is the point such that speed again becomes synchronous. Okay. So speed was decreasing from 1500 rpm. After reaching point C, speed again becomes 1000 rpm. Then if we try to go beyond C, then what will happen is PE is greater than PS1. Okay, then d square delta by dt square is greater than 0, sorry, lesser than 0. So rotor will decelerate. Now at C, speed is equal to omega s. If it decelerates further, or the speed further reduces, speed will become less than omega s. So d delta by dt will become less than 0, delta will reduce. That is, we will start coming back from C towards A if delta starts reducing. So we will go from A to C as delta will keep on increasing until speed is greater than omega s. But when now speed becomes less than omega s, how it becomes less than omega s? Because rotor was continuously decelerating. At C, the speed goes to synchronous. Beyond C, it will reduce below the synchronous, which will cause the delta to reduce. And we will move from C to A. Now when we are moving from C to A, first we will go from C to B. So when we are going from C to B, electrical power is definitely greater than shaft power. So d square delta by dt square will be lesser than 0. Let me write down the equations here. And now at C, speed was synchronous. From C to B, speed will decrease. So rotor decelerates. And if its speed reduces, at C it was omega s. So while going from C to B, it will be less than omega s because it is reducing below synchronous speed. So d delta by dt will be less than 0 and delta will go on reducing. So if I assume that at C speed was 1000 rpm, that is synchronous, now it will go on reducing till B. Let us say at B we have 500 rpm. Okay. So now when we will go from, we will consider the case of at the point B. Now when we will consider the point B, PS1 is equal to P. So d square delta by dt square is 0. So speed is constant. But see, if we see the speed, it is 500 rpm, which is less than synchronous speed, due to which d delta by dt is less than 0 and delta will further reduce. That means still even while coming back, I do not stop at B, I will go beyond B. So when we are going from B to A, what will happen is that electrical power is less than shaft power, due to which d square delta by dt square will be greater than 0. So rotor will accelerate. Now at point B, we have a speed equal to 500 rpm. If rotor will accelerate, it will start increasing, but still it will be less than synchronous. So d delta by dt will be less than 0. Delta will reduce. Okay. Again at A, I will consider that the speed becomes equal to omega s. So that is called as your second swing. Earlier when we were considering the case when we were going from A to C, that is called as first swing. While coming back from C to A, it will be called as second swing. Okay. And when applying equal area criteria, we only apply to the first swing because it is also called as first swing stability criteria. Now understand one thing here, how does my speed vary? When we were going from A to C in first swing, when we were going from A to C, A to B, omega was increasing, B to C, omega was decreasing. So how it was varying like this? That means at B we have a maxima omega max. But at second swing from C to B, speed was reducing. From B to A, speed was increasing. That is, it was like this. So at B we had a minima. That is, in first swing we get the maximum speed at B, and in second swing we get minimum speed at B. But at both ends C and A, we have speed equal to synchronous speed. Okay. Omega max or omega min, depending whether you are considering first swing or the second swing. Now let us consider how to apply the equal area criteria to this problem. Now if you see, when we were going from A to B, speed was increasing, so the area is called as accelerating area. And when speed is reducing from B to C, we will call it as decelerating area because speed was reducing. Now when we are considering the area, we are taking the area between PM and PS, because area was to be accelerating power. Now when we are considering accelerating power, it is actually shaft power minus electrical power. So from A to B, this area A1, because this is my shaft power, this is electrical power, so this area A1 represents accelerating area. It will be PS1 minus P, which is equal to P max sine delta d delta from delta naught to delta 1. This is my accelerating area. Now from delta 1 to delta 2, that is from B to C, speed was reducing. So this area here between electrical power and mechanical power represents A2, that is decelerating area. So that is your delta 1 to delta 2. PS1 minus P max sine delta, it will be A2. So A1 plus A2 must be 0. Okay, that is delta naught to delta 1 PS1 minus P max sine delta d delta must be equal to, plus delta 1 to delta 2 PS1 minus P max sine delta must be 0. And if we simplify this, if we take one area on the right hand side, should be equal to delta 1 to delta 2 P max sine delta minus PS1 d delta. Now what does it represent? If you see from B to C, obviously P is greater than PM. So to make the area positive, you have to subtract PM from P. That is, you have to subtract mechanical power from electrical power. This term is called as accelerating area. This will be decelerating area. So it states that accelerating area must be equal to decelerating area. Here both values will be greater than 0, because for A2, P max sine delta is greater than PS1. So it will be positive. For A1, PS1 is greater than P max sine delta. Hence it is called as equal area criteria. It states that the total area under the accelerating power curve must be 0. So the area in which the rotor accelerates should be the same as the area in which rotor decelerate. So that is why it is called as equal area criteria. Okay. Otherwise, it should have been called as zero area criteria. But now, this is fine how to apply equal area criteria. How do I know when the system will be stable or unstable? Now, What was the significance of point C? At point C, it was such that omega became equal to omega s. While going from B to C, speed was reducing. At C, it became equal to omega s. Now, consider this case when C lies here. That is, delta 2 is like this. Okay, I am not considering delta 2 here. Now, speed will go on reducing from this point to this point. Now, suppose C was beyond this point. Then what happens? Let me call it as x point. Suppose at x, speed is not equal to omega s, but rather speed is greater than omega s. That is, speed was reducing from b to x, but still it hasn't reached omega s. Then d delta by dt will be greater than 0. So delta will increase. That is, we will go beyond x. Now, when we go beyond x, this is my electrical power, but mechanical power is this much. So electrical power becomes less than mechanical power. If electrical power becomes less than mechanical power, then d square delta by dt square will become greater than 0. So speed will increase. So here what happens is, speed is still greater than omega s and it increases further. So speed will never be equal to omega s. So system loses synchronism. That is, C point cannot be beyond this point where x is present. Okay, C cannot be beyond x, because if speed does not reach its synchronous speed at point x, then it can never attain synchronous speed and it will permanently lose synchronism. So what is the angle of this point x? In case of sine, we get the same value at an angle theta as well as at an angle pi minus theta. So, if this is delta 1, this angle will be pi minus delta 1. So, we will say that the maximum rotor angle will be equal to pi minus delta 1. So, equal area criteria will get converted to delta naught to delta 1, ps1 minus pmax sine delta d delta should be equal to delta 1 to pi minus delta 1 pmax sine delta minus ps1 d delta. So from here what I can find out is ps1. How does it help? It gives me a fair idea of how much change can you make in the shaft power suddenly, so that system does not lose synchronism. If ps1 is greater than that, then system will lose synchronism. Okay, so it gives me an idea about that, the loading limit of the alternator that you can put on suddenly. Because what was happening in steady state was we were gradually increasing the load, but here we are suddenly increasing the load. So how much load can you put suddenly on the shaft or on the electrical terminals of the generator? That gives me an idea about that. Okay, so always remember delta max will be equal to pi minus delta 1, or delta max is such that if rotor angle goes beyond that, system will lose synchronism. Let us consider the next case when the fault occurs near the bus. So here what is happening is, this is my transmission line, this is infinite bus bar, this is my short transmission line. Now if fault occurs near the bus, the reactance up to fault will be equal to the reactance of the generator, because there is no reactance of the transmission line, but reactance up to load is equal to xd plus x line, which is much greater than xd. So what we will consider is, since we have a low impedance part to the fault, we will consider entire current goes into fault. Okay, that means power transfer to the load becomes 0. And as I told you, During fault, what was happening is electrical power equal to P max to sine delta. Now since I am saying entire current goes into the fault, the electrical power is 0, which implies P max 2 is 0. Okay. P max 1 will be when there was no fault. It will be, let us say this is XD, this is X line. It will be mod E mod V upon XD plus X line. Okay. What will happen when the fault is cleared, that is after the fault? How to clear the fault? There will be a circuit breaker here. We will open circuit. So here we will have a circuit breaker. We will open circuit this to remove the faulty part. So after the fault is cleared, then what will be P max 3? Again it will be mod E mod V upon XD plus XL. So that means X3 is equal to X1 is equal to, what is there, XD plus XL. So P max 1 is same as P max 3. Why it is same as P max 3? Because after the fault the original network is restored, so the maximum power capability becomes equal to the initial value. Okay, so these are the three cases, that is before the fault, during the fault and after the fault. So here what we will consider is shaft input remains constant. So shaft input will be taken as constant value. So initial operating angle will be such that in steady state I told you P max 1 sine delta naught should be equal to PS, that is shaft power should be equal to electrical power. So delta naught will be sine inverse shaft power by P max 1. This will be the initial operating angle of the alternator. Now let us consider the power angle curve and try to understand how does the system oscillate. So this is the power angle curve. Don't go beyond point A first of all. Concentrate your attention to this point A. So here what is happening is, this is my mechanical input, that is represented by PS0. Okay. Here shaft input will remain same. Okay. So at A, initially system is operating in synchronism, omega is equal to omega s and PS naught is equal to P. Now suddenly fault occurs. As I told you, entire current will go into the fault. So electrical power is reduced to 0. None of the power will be transferred to load. So, but delta is constant because delta cannot change suddenly. It is the angle between a synchronously rotating frame and the rotor. Due to rotor inertia, this angle cannot change instantaneously. Delta remains constant but electrical power is reduced to 0. So we move from point A to point B. We suddenly jump from point A to point B, that is electrical power becomes 0 but keeping the delta same. Now if you see, this is my shaft power, this is my electrical power, that is 0. So at point B if you see, PS naught is greater than 0, which is equal to P. So again let me write down the equations that we will use. Then okay, since PS naught is greater than P, d square delta by dt square is greater than 0, rotor will accelerate. Now initially the speed was equal to synchronous, now it will become greater than synchronous. If it becomes greater than synchronous, then d delta by dt will be greater than 0. Delta will increase. But until and unless the fault is cleared, electrical power will remain 0. So that means electrical power is 0, still delta is increasing. So we are moving from point B to point C. That is, we are increasing delta, keeping the electrical output 0. So as we go from B to C, what is happening is electrical power is 0. If electrical power is 0, shaft power is greater than electrical power. So d square delta by dt square is greater than 0. So speed increases. And it is greater than synchronous, so delta also increases. Now suppose at point C, fault is cleared. So what will happen is, when fault is cleared, we will enter the case of after the fault. So P max 3 will be equal to P max 1. Okay. So power will become equal to P max sin delta. But since delta cannot change instantaneously, so we will jump from C to D. Okay, because this is the curve representing P max sin delta. If delta is equal to delta C, we will go from C to D. We will jump from C to D directly. Okay, because delta will remain same, but power will suddenly change as we go from during the fault case to after the fault. Now if you see at point D, electrical power is greater than shaft power, because this is the shaft power and this is my electrical power. Since it is greater than shaft power, what is happening? D square delta by dt square is less than 0. So speed will reduce. But up to point C or D, speed was continuously increasing. So it will be greater than synchronous. Suppose at point A, speed is 1000 rpm. Up to point C or D, speed was increasing, so it becomes 1500 rpm. Now it will start reducing. But until it reaches 1000 rpm, it will be greater than omega s. So delta will increase. That is, if delta increases, we will go from D to E. Okay. Delta will keep on increasing and the speed will go on reducing. Now suppose at point D, again my speed becomes equal to omega s. This is E point. Speed again becomes equal to omega s, but PE is greater than PS naught. So d square delta by dt square is less than 0. So that means speed reduces, or we can say omega decreases. If omega decreases, it will go less than omega s. So d delta by dt will be less than 0. So delta will also reduce. That is, we will start going back from point C to point E towards point D. So this is called as first swing. When we go from A to B to C to D to E, because delta was keeping on increasing. Now delta will reduce. That is the case of second swing. So when we talk about second swing, now we will not follow the path like this. Why? Because once the fault has been cleared, we cannot again go back to the points B and C. Electrical power cannot become 0, because once you have removed the fault, the current will keep on flowing to the load and electrical power will be non-zero. So from E to point F is actually same as point A. From E to F, what is happening? Electrical power is greater than shaft power, because this is my shaft power. So d square delta by dt square is actually less than 0. That means omega reduces. Now at point E, speed was synchronous speed. If omega reduces, it becomes less than synchronous, due to which d delta by dt becomes less than 0 and delta also reduces. Okay, so delta reduces, we are going from E to F. At point F, what happens? Electrical power becomes equal to PS naught. So d square delta by dt square becomes equal to 0. Speed becomes constant. But since speed was continuously decreasing from E to F, this speed is still less than synchronous speed, due to which d delta by dt is lesser than 0, delta will further reduce. That is, again we will go beyond the point F. Now while we are going, we will go from F to G. Now when we are going from F to G, what is happening? Electrical power is less than shaft power, due to which d square delta by dt square will be greater than 0, which means speed will increase. But up to point F, the speed was continuously decreasing. Let us say it is 1000 rpm, here it becomes 500. So it will increase, but until it reaches 1000 rpm, speed will be less than omega s. D delta by dt is lesser than 0, delta will go on reducing. So G is a point where the speed will again become equal to 1000 rpm. Now I have shown G for a negative value of power. How does that happen? Because G will be the point until these two areas become equal. The areas becoming equal signifies that the acceleration is equal to deceleration. Whatever is the increment in speed is same as decrement in speed. Okay. From E to F, the speed is decreasing. So if it goes from 1000 to 500, then from F to G it must go from 500 to again 1000. Increment must be same as decrement. So it will keep on reducing until the speed again becomes equal to synchronous. And that point even may be negative. That is not an issue. Now let us see how delta and the power angle vary. Speed and the power angle vary. First, let me plot omega versus t. Now, initially, the speed was equal to omega s at point A. Okay. Then, when the fault occurred, we moved from A to B suddenly, and from B to C, the speed was increasing. Now, when the fault is cleared at C, we move to point D, and from D to E, the speed was decreasing, and it again becomes equal to synchronous. This is at point E. This was the case of first swing. Then from point E, the speed kept on reducing until point F. And again from point F to G, it goes to synchronous. Like this. So at point C, we will have omega max. At point F, we will have omega min. Okay. How does my power angle vary? Now, initially at point A, power angle was equal to delta naught. Now, when we were going from A towards the point E, okay, up to, that is in the first swing, from A to point E, power angle continuously increased. Okay. Then from E to G, power angle reduced, and at point F it became equal to delta naught. That is, point F was identical to A, and at G it was negative. Okay, that is how your power angle delta will vary. Again it will start increasing like this. So this is your point A, this is point E, this is F, this is G. Okay, so that is how my power angle delta can vary. It will go on increasing till E, then it will go on reducing till G, and again it will start increasing. So remember, in the first swing at C and D, we will get the maximum speed. So now let us apply the equal area criteria to determine the stability criteria for this system. Now, as I told you, The critical case will become equal to when the final value of delta is equal to delta max. How? First let me show you the general case of equal area criteria. This is my power angle curve, P max sine delta, and this is my PS naught. This is my initial operating angle delta naught. When the fault occurred, we were going from B to C. When the fault was cleared, we jumped from C to D and we went till E. So this will be my accelerating area, the area between PS naught and PE from B to C. Because from B to C speed was increasing, so that will correspond to accelerating area A1. But from D to E speed is decreasing, so this area corresponds to decelerating area, that is A2. Now the critical case for stability will be when this point E is identical to point, let us say, X. When E becomes equal to X, that is my critical case, because E is a point where speed becomes equal to omega s. If E is lying beyond X, then what will happen? Beyond X, electrical power goes less than shaft power. So d square delta by dt square will be greater than 0. So speed will increase. That is, if speed does not go to synchronous speed up to point X, then beyond that it will increase further and it can never reach synchronous speed. So system will lose the synchronism. That is why at the most E can lie at the point X. Okay. So what will happen then? This will be my decelerating area. So X is corresponding to delta 2, or let us say delta max, which is equal to pi minus delta naught. Okay. As I told you, when two points are symmetrical, one is theta, other is pi minus theta. So now let us apply the equal area criteria. So area A1 can be calculated as integral delta naught to delta C PS naught minus 0, because electrical power is 0, plus delta C up to delta max PS naught minus electrical power is then P max sine delta. This must be 0. So this will be PS naught into delta C minus delta naught plus PS naught delta max minus delta C. Sine delta integration is minus cos delta C up to delta max. This must be 0. Now if we substitute the limits in the integration, so it will be, this term will get cancelled out. So PS naught delta max minus delta naught plus P max cos delta C minus cos delta max must be 0. So from here, if we try to find this, this will be with the minus sign because it was PS minus PM. So if we try to find P max cos delta C, it will be PS naught delta max minus delta naught plus P max cos delta max. So cos of delta C will be PS naught by P max delta max minus delta naught plus cos delta max. So delta C will become equal to cos inverse, PS naught or mechanical power by P max. Delta max was pi minus delta naught, so it will become pi minus 2 delta naught. Cos delta max will be cos pi minus delta naught, that is equal to minus cos delta naught. So this will be my critical clearing angle. This angle means the maximum angle at which the fault can be cleared. Otherwise, what happens is, if you clear the fault after this angle, suppose this is my delta CR, critical clearing angle, but I clear after this. Okay. Then at critical clearing angle, this area is same as this area. But if you clear the fault at this angle, let us say delta C, which is greater than critical clearing angle, then what will happen? This will be my accelerating area and this will be my decelerating area. Now if you see, accelerating area A1 increases and decelerating area A2 reduces. That is, acceleration is more than deceleration, or the increment in speed is more than decrement in speed. So overall speed will increase and it will not go equal to synchronous speed. So speed will be greater than synchronous speed and system loses synchronism. That is why fault can be cleared at the most equal to delta CR. Okay. If it is cleared before delta CR like this, then what will happen? This will be my accelerating area and decelerating area will go over somewhere here and system will be stable. Then delta 2 will not go equal to delta max. It will stop before that. System will be stable. Okay. It is not necessary that you always go up to delta max. Delta 2 must be less than or equal to delta max. And remember, in this equation, all the angles that you will use will be in radians. Okay. So that is why critical clearing angle is the maximum angle at which the fault can be cleared. But one problem with this specification is, I cannot tell the manufacturer that this must be critical clearing angle. Rather, the speed of circuit breaker will be specified in terms of time. That is, time of clearing the fault. So let us define critical clearing time. This is the maximum time at which the fault can be cleared. Now swing equation can be written as md square delta by dt square is accelerating power. Now during the fault, what happens is, accelerating power, which is equal to PS naught minus P, will be equal to PS naught, because P is 0 during the fault. During the fault, that means from point B to C or from point delta naught to delta C. Okay, PA will be equal to PS naught. So d square delta by dt square will be equal to PS naught by m, which is a constant. If we integrate both sides, what we will get is d delta by dt is PS naught by m into t. Integrate again, we will get delta, which goes from delta naught to delta C. We will have time. If fault occurs at t is equal to 0, we will go from, integration will be t square by t. We will go from t naught 0 to tc. Okay, assuming that the fault occurs at t is equal to 0. That is, at t is equal to 0, I am at point B, which is equal to delta naught. So delta C is equal to delta C minus delta naught is equal to PS naught by m or 2m Tc square. So Tc will be 2m by PS naught delta Cr minus delta naught. This will be my critical clearing time. Okay. Remember, we were able to integrate like this because PE was 0 and accelerating power is independent of delta. So we were easily able to solve this differential equation. If during the fault power was non-zero or it were dependent on delta, then this sort of critical clearing time calculation is not possible. We have to use numerical methods to solve the differential equation. Now we know m is equal to gh by pi f. So critical clearing time will become 2h by pi f ps naught delta cr minus delta naught. But here this ps naught will be in pu, because ps naught upon g will give me per unit power of the shaft input. So let us summarize what we covered in this lecture. We saw two cases: increasing steam input. There I explained how does the rotor oscillate. We made use of two equations. One was the swing equation and other equation was d delta by dt is equal to omega minus omega s. And we saw that here we can find the PS1, which meant how much the shaft power can be increased suddenly without losing stability. Then we saw the case of fault near the bus. In that, what we tried to find was, first we saw oscillations, then we determined critical clearing angle, cos inverse Pm by Pmax delta max minus delta naught plus delta max. Okay, and we determined critical clearing time, that is under root 2m by ps naught delta cr minus delta naught. Okay, so remember here angles are used in radians and these are critical clearing angle and time. And in the case fault occurs near the bus, after the fault is cleared, original network will be restored and Pmax3 will be equal to Pmax1. That is the characteristic of this type of fault. We will consider some other cases in the next lecture to determine the transient stability.